All right, questions? My day's going really good. Really good. Hey, I got a Coke. I don't normally drink caffeine, but I'm going for it. All right, well, so we played with weird stuff on Wednesday with cardinality and things like that. So coming back to a little more solid ground today. And we're going to probably wrap up set theory today. So just talking about some odds and ends, unions and intersections of more than two sets. I want to talk about functions, and we can understand functions through the language of sets. I want to talk about summations and sequences and review matrices, and that'll probably do it for sets. So I posted homework on set theory back on Wednesday, which is due the following Wednesday. Any questions on that homework set? It's mostly set operations and things that we've already covered, which you need to know. But it's just to get some practice on these things. So you've seen summation symbols, right? Sum from I equals 1 to 5. So you do whatever is inside there with I equal to 1, 2, 3, 4, and 5. We can do the same thing with union. We can say, for example, the union from I equals 1 to 5 of AI, and I'm supposing that we have a series of sets defined here. For example, A1 might be the set 1, 2, 3, and A2 might be some other set. And we can use this symbol as a shorthand for A1 union A2 and so on, up to and including A5. So it's a way to take all of this and express it more succinctly, just like this is a way to express this plus this plus this 5 times more succinctly. And we can do intersections the same way. But it lets us pose some interesting questions. So I'm going to define a family of sets here, a collection of sets, AI, where A sub I is the set of integers starting with I. So what would the elements of A1 consist of? What does the set A1 look like according to this definition? Say again? 1. Anything else?
Just 1 all the way through
all the integers from 1 on up. What does the set A2 look like? It's from 2, 3, 4, 5, 6, and so on. Okay, so we have an intuitive idea what set A sub I is. It's all the integers starting from I and going on up. And I have defined an infinite number of these sets, A1, A2, A16, A512. Any I you pick bigger than or equal to 1, there's a corresponding A subset I, A subscript I corresponding to that. This is a family of sets. And we can ask questions about this family of sets. For example, suppose n is some integer bigger than or equal to 1. The union from I equals 1 to n of A sub I, what do you think that looks like? How could we describe this union? So think about this for a minute and discuss it amongst yourselves and make some hypotheses. if you have an idea, shout it out.
Just be the integers 1, 2, 1, 2, 3, 4, 5.
Just the integers 1, 2, 3, 4, 5, which is just A1. Does that seem reasonable? That's in fact what this union is. Because a union is just a collection of all the stuff from all the sets taken together. Well, every one of these sets, A2, A3, A4, is a subset of A1. So anything I find in A2, I already find in A1. Anything I find in A3, I already find in A1. So when I take all these things and I put them together, I'm not adding anything new to A1. So this is just going to be precisely A1. And that's not too mysterious once you think about it from the answer working backwards, right? The union of all the integers from 1 on up, and all the integers from 2 on up, and all the integers from 3 on up. That's just the integers from 1 on up. Okay, what about the intersection?
Just be 1.
Well, let's see. So 1 belongs to set A1, right? But it doesn't belong to set A2. So to be in the intersection, it's going to have to be contained in all of them. But I think your thought process is in the right track.
It should be the empty set, right?
So empty set or A sub n?
Oh, it's right, because that is not empty set.
So this would be A sub n. So if I take the union of A1, A2, and A3, I'm just going to get A3. Because, again, this is a subset of A2, and it's a subset of A1, and A2 is a subset of A1. So in some sense, it's the smallest of all the sets that we're putting together. Although we know smallest can get us into trouble. But, you know, it's the set that starts the furthest. That's just equal to AN. All right, now I can do this union with an infinity on top. And there is no such thing as A infinity, because that would be the integer starting from infinity, and infinity is not an integer. This means something different. This means we want A1 union A2 union A3, and we want to keep going forever. So it's the union of every AI for all I bigger than or equal to 1. There's no integer bigger than or equal to 1 such that AI is not part of this union. It's the union of all of these sets. And what is that going to turn out to be?
A1.
That's still A1. Even though we're adding an infinite number of sets of things, they're all subsets, so it's still just going to be A1. All right, the infinite intersection, which is the intersection of all of these sets. And it's not going to be A infinity, because A infinity is not a set, because infinity is not an integer bigger than or equal to 1. Empty set. What do you think about the empty set? So why the empty set?
Because for every next I you go to, there's another number that isn't within the set. There's always another number. Not
Perfect.
within the set.
If you pick any integer and you say, I think that integer belongs to this, I think that the number 17 belongs to this, all you got to do is look at the fact that 17 would also have to belong to A18. And it doesn't, because A18 starts from 18 and goes up. And if you think 5,000 must be in this intersection, well, this is also the intersection taken with A5001, which doesn't contain 5,000. And so any integer that you think of is missing from at least one of these AIs. In fact, it's missing from a whole lot of these AIs. And so any integer that you think of cannot be contained in this intersection. And so you're forced to conclude this intersection must be equal to the empty set. And that's worth noting. When we do an infinite union, it doesn't seem to change our answer. When we do an infinite intersection, it changes our answer dramatically. Because any number of AIs that we intersect, we end up with an infinite set. Right? The set of integers starting from n and going up forever. But when we intersect all of them, we end up with a completely empty set, which is kind of the other extreme of an infinite set. And that might suggest somehow that infinite unions and infinite intersections are different somehow. And this is another branching point to this area of mathematics called point set topology, which is like the abstract version of calculus. And that can be built up on the notion of infinite unions and infinite intersections behaving differently. So this is kind of central to something. All right, does that make sense? Using this notation for intersecting multiple sets. All right, and so summations kind of the same thing. If you have some function that depends on I, we can ask for the sum over I equals 1 to 5 of fi. And this is just a shorthand. Well, could that be air conditioning?
Is that finally working?
That would be awesome. Or it's the aliens coming for us. On their air-conditioned spaceship. So this is just a shorthand for F1 plus F2 plus F3 plus F4 plus F5. Okay, that's all it is. And it doesn't have to be from 1 to something, it can be from m to n, and that's fm plus 1. And we're assuming n is bigger than or equal to m here, so that this makes sense. And one thing to note, question?
Sorry, I think this is kind of a setting, but with the summation, is there a way to say what your increment is? So like if you wanted to go from 10 to 5, all of
I don't think there is in a standard summation symbol, but you can fake it.
Okay.
Right, so we could do sum from I equals 1 to 5 f of 2 times I, and that would be 2, 4, 6, 8, 10, or 2I minus 1 to be 1, 3, 5, 7, 9.
Couldn't you do something like I does not equal I plus 1 or something like that in the summation? So I equals 1 and then I does not equal I plus 1.
So you can multiply by like a Boolean that's 0 or something?
Yeah, because you see that with like, say you have an I and a J, and J doesn't equal I.
Yeah.
You do the same thing with I.
Yeah, you could do something like that probably. Yeah. Yeah, we'll do something like that in a minute too. So the I is arbitrary, right? Sum from I equals 1 to 5 of fi is exactly the same thing as the sum from w equals 1 to 5 of fw. It's just a placeholder. And this is basically a for loop, right? In code, this is just for I equals 1, I less than or equal to 5, I plus plus, sum equals sum plus fi. Initialize sum to 0. And in a for loop, you're usually using I, but sometimes we use J or K or W. And it makes no difference as long as we're consistent in the use of that. This is also the sum from W equals 11 to 15, f of W minus 10. Right, because when W is 11, we're going to add f of 1. When W is 12, we're going to add f of 2. When W is 15, we're going to add f of 5. It's exactly the same thing as this. So we can change the indices of summation which is sometimes useful to do. We could also do the sum over I is contained in the set 1, 2, 3, 4, 5, f of I. And that's a little silly because we could just do that, but if this was some other set, right, we could list a set and we could say, do the summation where I varies from each element of this to another element of this. The order is presumably unimportant, which is good because addition is commutative. And there's various properties of these things. If I'm going to add up the value of f of I plus g of I from 1 to 5, that's the same thing as adding up the f of i's and then adding up the g of i's and then adding those sums together. So that's a bit of associativity and commutativity in there. And if we're adding up some constant multiplied by a function, that's the same as a constant multiplied by the sum of just the function. Is that tickling any memories for anyone?
Oh,
Yeah. So this is also how integrals work, right? If you have an integral with a constant, you can pull the constant out. If you have an integral of a sum, you can break it into two integrals and add them. Why does that work? Because integrals are just summations, right? It's just a whole lot more summations of smaller things. So this is good stuff. And of course we can do the sum to infinity. And it means add up forever. And sometimes that's reasonable and sometimes it's not. If we do the sum from I equals 1 to infinity of I squared, that just gets bigger and bigger and bigger. So we would write down that's equal to infinity, by which we would mean this gets bigger and bigger and bigger, and eventually it's bigger than any number you can think of. But some teachers will frown at you if you write that. This, on the other hand, is the perfectly reasonable thing to write. So the sum of 1 over 2 to the I, well, that's 1/2 plus a quarter plus an 1/8 plus a 1/16. And as you add more and more things, that gets closer and closer to the number 1. It never reaches it, but it gets closer and closer, and so then we start talking about limits and all that sort of stuff. We would say that in the limit, this is equal to 1. It's what? Yeah, I'm going to take a number actually, and then we'll see it in the other class. Yeah, that's probably what it is. But I have more elaborate beliefs. 75.8. Exactly. All right, so the other thing you can do, and you have some homework questions on some of what we've just said. The other thing you can do is you can nest your summations. You can say, for example, the sum from I equals 1 to 5, or the sum from j equals 2 to 3, of some function of I and j. And if you're asked to do this, one way to think about it is to throw in some parentheses. These are actually brackets. And just look at this inner piece. The sum from j equals 2 to 3 of f of I comma j. Well, that says set j equal to 2 and evaluate that expression. That's f of I comma 2. And then set j equal to 3 and evaluate that expression. That's f of I comma 3. And add them together. That's what that inner summation evaluates to. And now we've just got the sum from I equals 1 to 5 of a simple expression. So set I equal to 1, and then set I equal to 2, and do that all the way up to I equals 5. And that's what that double summation is equal to. So you can break it up like this. And this is like a nested loop, right? For I equals 0, 1, I less than or equal to 5, I plus plus. And in your curly brackets, you're saying for j equals 2, j less than or equal to 3, j plus plus. And then you're adding this expression to a running sum. All right, so any surprises, worries, concerns there? I made my fancy portable podium also, so I don't have to carry my camera around. All right, let's talk about functions. Oh, they're spinning up to break orbit. So we know what functions are, right? Mathematically, sine of x is a function. You give it an x, it gives you back a value we call sine of x. Computer science, a function is a set of code. You give it a set of arguments, it gives you back a return value, unless it's void. But kind of more abstractly, we can think of a function as a mapping. So a function f, and I'm going to write f colon a arrow b, is a mapping, or an assignment, of an element of B for each element of A. So for any little a contained in the set A, we write f of A, and f of A will be an element in the set B. And this is to show that f maps A to f of A. And so if we think of this in pictures, here's a set A, here's a set B. Here's an element of set A, f takes that element to some set B, some point in the set B. here's another element of A. F maps that to some point in B. And here's a third element. And it maps that to a third element. So that's a function. Now, to be a well-defined function, we can't allow this point in A to map to more than one place in B. F has to take it to exactly one location in B. This is what it means to be a well-defined function. So we could say this point goes here. We could instead say that this point goes there. But we can't say that F takes this point to both that and that. If it takes a point to more than one place in B, it's not a function. So this is the vertical line test that you encounter in other courses. And if these A and B are real numbers, for example, we're saying that F of 5 has to be one value. It can't be both, 7 and 8. It's got to take you to one value. But what can happen is we could have some numbers in B that don't get mapped to from anywhere. And we could have some numbers in B that are mapped to more than once. Both of those things are allowed. So this leads to some definitions that we've touched on before. So if every point in B equals f of A for some A in A, say if each point in B is mapped to by something in A, then we say F is onto or surjective. So onto means that F basically maps onto every possible point in B. We don't have this situation where there's some points that aren't being mapped to. So that's one type of function. Another type of function is called injective, or one-to-one. So if distinct points in A always map to distinct points in B, then we say that this function f is one-to-one or injective. So injective means that we don't have this situation where two different points are going to the same place in B. In other words, different points here map to different points there. That's an injective function. Two points map to the same thing, that's not injective. So it's injective if every pair of points in A maps to different points in B. Okay, so let me give you an analogy. Here's my food analogy. Got a birthday cake, somebody's birthday, and you've got a bunch of people. Big people. right, so you're going to cut the cake into pieces and you're going to hand out pieces to people. Okay? So F maps pieces of cake to people. If F is surjective, that means everyone gets a piece of cake. Okay, surjective function. Everybody over here is going to get a piece of cake. In other words, F maps to every person over here. If F is injective, nobody gets two pieces. This person might get a piece of cake. If it's surjective, they will definitely get a piece of cake, but they're only going to get one piece of cake, right? If F maps two different things over here to the same person, then this person would get two pieces of cake. So to say it's injective means nobody's getting two pieces of cake. So if you think of your map or your function F as take a piece of cake, assign it to, hand it to whoever that's mapped to, right? Surjective means everybody gets mapped to, everyone gets a piece of cake. Injective means nobody gets more than one piece of cake. And it can be both. If it's both, then it's bijective. Or one-to-one and onto. If you have 5 pieces of cake and 50 people, then it's definitely not surjective, because there's going to be a bunch of people who don't get any cake.
Would it still be injective at that point?
It could be, but you might take all 5 pieces and give them to you, right? And now it's not injective either. And there might be 5 pieces of cake and only 2 people, and it still might not be surjective, because all 5 pieces might go to one person. And if there's 5 pieces and 2 people, it's definitely not injective, because somebody's going to get more than one piece of cake. So another way to think of this, if you look at things that map to something over here on the receiving end, if your function is surjective, the number of things that map, the number of pieces of cake is always bigger than or equal to 1. Could be 1, could be bigger than 1. If it's injective, it's always less than or equal to 1. If it's bijective, it's exactly 1. That's 1-to-1 onto. So if you take a function that's mapping from a set A to a set B, if the function is surjective, then every point in B is mapped to at least once. If the function is injective, every point in B is mapped to at most once. And if it's bijective, every point in B is mapped to exactly once. So those are just definitions. We'll come back to them once in a while. And it's easier to have a definition than go through an explanation. But this pops up in other courses, and you've probably seen this before, and you'll see it again. Okay, a few more definitions. So f is a function from A to B. A is called the domain. It's the set that we're mapping from. And B is called the codomain. And if little a is contained in the set A, then we can say f of a is the image of little a. And so we're kind of thinking of this as projecting from A to B. Right, here's this point in A, there's the point that it projects to in B. So we can call f of a the image of A, and we can call A the pre-image of f of A. Sweet?
I don't think that's the answer.
No, I don't think so. If it is, we got bigger problems. So f of a is the image of A is the pre-image of f of A. It's the thing that is going to project or map to f of A. And if we write f of the set A, which is the set of all f of A, where A is an element of A, I should have used a different variable. The set of all f of little a, where little a is an element of big A. So the collection of all the things that get mapped to from A, that's called the image of the set A, which is also called the range of the function f. It's sometimes called the image of f. So domain and range are usually what we talk about in other math courses. And the range of a function is just the collection of all the things that it maps stuff onto. And so examples. Let's take x over the real numbers. It's real number Friday. Let's take x over the real numbers and let f of x be the function which takes x to x squared. And let's suppose that f is supposed to go from the real numbers to the real numbers. So is f injective? Does it take different numbers here and map them to different numbers there?
No.
Why not?
Negative and positive map to the same.
Right, so it's not injective because f of minus 5 is the same as f of 5. So two different points in the domain and they map to the same place in the codomain. That's not injective. Is it surjective? Does everything get mapped to from somewhere? Yeah, no, maybe.
Could you map to like the square root of 2? If you couldn't, then it wouldn't be on 2.
Right, but the fourth root of 2, if you square that, you get the square root of 2.
Should be good.
So that's good. But there's no number that maps to -1. So it's not surjective either. But if I map from R to the set of non-negative real numbers, I'm just using R plus to say the real numbers that are not negative, suddenly this is surjective, because every number that's bigger than or equal to 0 is the square of some real number. So surjectiveness kind of depends on what the domain is. Right? I could take a function that's surjective and I could say, well, this function actually maps to the set of real numbers plus the set of vegetables. And suddenly my function's probably not going to be surjective unless square of x maps to broccoli or something. So surjectiveness really depends on the domain, but injectiveness is a little more interesting. So f of x equals 2x, going from the real numbers to the real numbers. That's a nice injective function, right? Because if I have two different numbers, then there 2 times those numbers are going to be different also. If we wanted to get chapter 3-ish on this, f is injective if and only if f of x equals f of y implies x equals y for all x comma y in the domain. F is injective if the only time that f maps things to equal values is when the two things being mapped are the same. So if f of x equals f of y implies that x equals y, always, then we can say that f is injective. And if this condition is true, then we can say f is injective. If f is injective, we can say this condition is true. So it's an if and only if. So this is kind of the power of some of this propositional logic, right? It's like 3 pages of description I've been writing. And we can define functions lots of ways. We can define them with mathematical formula. We can say f of x equals leftmost digit of x, where f is a function from the integers to the set 0 up to 9. So f of 17 is 1, f of 2,512 is 2, f of 800 is 8. It's a perfectly valid function. For any number in z, I get exactly one number back from f. I get the first digit, first meaning the leftmost. It's absolutely not injective, because f of 2 and f of 20 are both going to map to 2. And it's definitely surjective because, well, just the numbers 0 through 9 will map to 0 through 9, so everything gets mapped to at least once. So it's surjective, not injective. And that's a weird function, but we can do it. I can define a function which maps from the integers to the set square triangle. Where I define f of x to be square if x is even and triangle if x is odd. That's a fine function. All right, and one more definition. If I say f of x equals g of x, let me change that. If I say f equals g, this means f of x equals g of x for all x in the domain of f, which must also be the domain of g. So to say two functions are equal basically says they're equal everywhere within whatever the domain of those functions is. And all of this stuff depends on how we set up the domain and the codomain. Because for example, I could have a function f f of x equals x squared and g of x equals x. And if f goes from the set 0, 1 into the set of integers, and g goes from the same set to the same set, on that domain f and g are the same function. Because f of 0 is 0, f of 1 is 1, g of 0 is 0, g of 1 is 1. So with this domain, f and g are equal, but clearly, if I defined f to go from z to z, and g to go from z to z, these are not the same function because f of 2 is 4 and g of 2 is 2. F of 10 is 100, g of 10 is 10. So the domain and codomain always come into play. Okay, did we talk about Cartesian products of sets yet? Okay, whereabouts here? So Cartesian products of sets. So let A and B be sets, and they could be finite or infinite, just any sets. So here's a definition. An ordered tuple is an ordered collection of things. So an ordered n tuple is an ordered collection of n things. Listed in parentheses. So the Cartesian product which we write as AXB of two sets A and B is, well, it's a set of all two tuples, parentheses little a, little b, where little a comes from set A and little b comes from set B. So the Cartesian product of two sets is a new set consisting of these ordered pairs, or ordered two tuples, of elements A comma B, where A comes from the first set and B comes from the second set. So examples. Let A be the set consisting of, I don't know, x and y, and let B be the set consisting of 2, 4, and 6. Okay, A cross B is going to be a new set. And it's going to be comprised of ordered pairs, two tuples, where the first thing comes from the first set. So for example, it could be the element x, And the second part of the pair comes from the second set, for example, 2. And it's the set of all such 2 tuples. So it could be x comma 2, x comma 4, x comma 6, y comma 2, y comma 4, and y comma 6. All right, so A cross B, the Cartesian product of A and B in this case, is a new set containing 6 elements. And each of those elements is an ordered pair. The first part of that pair comes from A, the second part comes from B. And we could do A cross B cross C, and we'd get 3 tuples, where the first element came from A, second from B, third from C. So we can extend this in general. And you might notice, if A and B are finite, then the number of elements in A cross B is the number of elements in A times the number of elements in B. We'll come back to that about week 7 when we talk about combinations and permutations. If your sets are finite or infinite, it gets more interesting. So suppose A is a set 1, 2, 3, and B is a set 1, 2, 3, 4. Well, I got 3 things and 4 things. I know that the Cartesian product of A and B is going to be something containing 12 pairs. And they're going to be 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, all the way up to 3, 4. And remember, each of these things is not a set. It's this new entity we're calling a tuple, or an ordered pair. And so there's a notion of a first number and a second number. Because the first number has to come from the first set, the second number has to come from the second set. So A and B. But if we were to draw a Swiss cheese number line, where we're only marking the integers, well, the set A contains these things. The set B contains 1, 2, 3, 4. But if we think of these tuples as being Cartesian coordinates, there's that word Cartesian, right? What are the elements of A cross B? Well, 1, 1, 2, 1, 3, 1, 1, 2, 2, 2, 3, 2. It's these 12 dots. Where, for example, this is 2, 1, and this is 3, 4, and this is 1, 1, and so on. Well, if we go back to real numbers for one more moment, and you remember interval notation, so this interval notation, 1, 2 inside square brackets, is the set of all real numbers between 1 and 2. And if I do parentheses here, that looks like an ordered tuple, but it's not. It's a different thing, same notation. But this is the closed interval between 1 and 2, which on the number line just look like this. and let B be the closed interval 3, 5. So it's all the numbers between 3 and 5 inclusive. Well, if you think of those as sets, right, infinite sets, and you think of their Cartesian product, you've got 1, 2, so you got 1, 3, you got 1.13, you got 1, 3.1, you got 1.001, 3.111, right? You've got every possible tuple where the first number is between 1 and 2 and the second number is between 3 and 5. Well, if we think of that on a Cartesian plane, where this is A and this is B, what does that whole collection of points look like? It's going to be this filled-in rectangle. The set of all points in that region where the x-coordinate is between 1 and 2, and the y-coordinate is between 3 and 5. And it's a closed rectangle because it includes the point 1, 3, the point 1, 5, the point 2, 3, the point 2, 5, in other words, the corners, and the edges. And if A was the open interval, the numbers between 1 and 2, but not including 1 and 2, and B was between 3 and 5, but not including 3 and 5, the shape would still be the same, except we draw a dotted line on the outside here, because it wouldn't include any of the stuff on the border. That would be an open region. Okay, so Cartesian product is named for Cartesian coordinates, right? We can think of what we do on the good old Cartesian plane as an extension of Cartesian product of sets. But we're not going to worry about real numbers for the rest of today. We're just going to think about sets, right? Which might sometimes be the set of real numbers. But A Cartesian product B is just all the ordered pairs, where the first thing comes from A, the second thing comes from B. Okay, so let's think about functions again. So let f A to B be a function from A to B. Well, we can specify this function with an equation, if it works that way. We can specify it in words, right? Pick up the last digit of the number when you write it in base 3. We can specify it with cases, right? We can say if this is the case, then the function is equal to this. If that's the case, then it's equal to that, and so on. Another way to specify a function is with an ordered tuple. So if we take A comma f of A, that ordered pair tells us the value of our function at the point A. And if we make a collection of all of these tuples, that's a single set that completely defines the function f. The set of all ordered pairs consisting of A paired with f of A, defined across every point in big A, that set is f. It's an explicit listing of what the function does to every point in its domain. So for example, if I want to describe the function x squared, I can do it by listing the following set. Let's just say this is f going from positive integers. Right? Here's an infinite set of tuples, which is exactly the function f. And if I want to know what the value of f is at some point, I just find the tuple whose first element is that point, and the second element is f of that point. So sets are more than just ways to list collections of objects. We can actually use them to encompass the meaning of a function. And this is a few years of my research life digging into that idea as a way that computers can evaluate functions by basically just looking up in these giant tables of tuples, right? Well, this is a collection of tuples where the first element comes from A and the second element comes from B. This is a subset of the Cartesian product of A and B. And every function is a subset of the Cartesian product of A and B. And some subsets of that Cartesian product are functions. Some of them aren't well defined though. Right? We could have one map to 1 and also have one map to 5. That's not a well-defined function. But every well-defined function is contained somewhere inside this Cartesian product. It's some subset of that. So the power set of the Cartesian product of A with B, that's the set of all subsets, all possible collections of tuples. And if each collection of tuples corresponds to a function, this is the list of all possible functions from A to B. So if I were to write the power set of R cross R, it's a big set, but contained in that set is every mathematical function that anybody will ever think of. Sines, cosines, square roots, hyperbolic arctangents, everything. Just a subset of R cross R. Just powerful stuff. And it's much more than just a set as a collection of pens or animals, right? You can use this to build up lots of mathematics. And that's one reason why it's fairly easy to get into paradoxes, right, like Russell. Because this stuff goes off in all these different directions. All right, so last thing I want to go over, and this will do us for set theory, is matrices. And we touch on matrices in ECS 120 when we're doing KVL, KCL, I said it, solving equations. And you touch on matrices in other courses. How many people here have taken or are taking Math 215?
Is that linear?
That's linear, yeah. So linear is 3 different subjects. One of those subjects is matrices. It's just the study of matrices and matrix operations. It's also simultaneous equations. It's also the study of hyperspaces. And they're all the same thing. So let me just do a quick review of matrices because it ties in some of this stuff. So what's a matrix? It's just some big parentheses with some numbers written down. There's my formal definition. Usually 2-dimensional, right? And it could be 3 by 3, or it could be 2 by 6, or it could be 1 by 3, or it could be 1 by 1. Okay, but it's you know, usually a 2-dimensional. And if we move down I spots, we get to the ith row. And if we move across a certain number of spaces, we get to the jth column. And so this element here might be element I comma j. And I've always thought of I as moving down. The first index moves down and the second one moves across. And it's partially from early exposure to Fortran. But it's a fairly standard convention. And so if this is our matrix A, we can think of it as a collection of elements A, I, J. So this suggests that our matrix actually looks like this: A11, A12, A13, A21, A22, and so on. And it's just useful to pin down an order of I and J to be able to talk about it. And so a certain number of rows and a certain number of columns. And so addition we can define pretty easily as long as our matrices are the same size. So for example, I might have 1, 4, 6, 2, 5, and -8. And here's another matrix, 3, 0, 0, and 2, 16, and 100. And if I want to add these matrices together, I just do it term by term. So 1 and 3 is 4, 4 and 0 is 4, 6 and 0 is 6, 2 and 2 is 4, 5 and 16 is 21, -8 and 100 is 92. So addition, no problem. Just go element by element. But it only makes sense if the dimensions of this matrix, the number of rows and the number of columns, is the same. Subtraction, exactly like addition, but subtract instead of adding. So 1 minus 3 is -2, 4 minus 0 is 4, and so on. Multiplication is where it gets interesting. So multiplication is not defined element by element. Right? You can do that, but it turns out to not be as useful as something else. So to multiply matrices, you need to have a certain property of the dimensions. So if this is an m by n, and you want to multiply it by another matrix, this matrix has to be n by something, k. And the result will be an m by k. So these inner dimensions need to match. Otherwise, multiplication is not defined. So if you have square matrices, n by n, you can multiply any of them by any other. But if you allow rectangular matrices, multiplication isn't even defined for some pairs. Okay, it's a quirky operation. But here's how we multiply. So this is 2 by 3. This next matrix has to be 3 by something. You can tell it's Friday. I'm doing really easy numbers. Okay, we're going to multiply this out. We're going to get a big matrix. It's going to be 2 by 4. So this is 2 by 3, and this is 3 by 4. We're going to get a 2 by 4.
That's 4 by 4.
That's 4 by 4. Let's do it like that. Okay, that works. I got carried away writing numbers. All right, so 2 by 3 and 3 by 4. So we'll get a 2 by 4. All right, so this first element up here, we're going to get by taking the first row of our first matrix and the first column of our second matrix. And we're going to do what's called a dot product. So we're going to do 2, 4, 6, dotted with 4, 2, 0. And a dot product just says multiply first by first, second by second, third by third, add them up. So 2 times 4 plus 4 times 2 plus 6 times 0. So that's 8 plus 8. That's 16. so weird nobody shouted out 420. It's like all my friends. All right, so the second element, first row, second column, is going to be the first row multiplied by the second column with a dot product. So the second entry is going to be 2, 4, 6, dotted with 1, 1, 2. So that's 2 times 1 plus 4 times 1 plus 6 times 2, and that's going to be 18. And you keep going. The entry down here, so second row, first column, is going to be the dot product of 1, 3, 5 and 4, 2, 0. 1 times 4 plus 3 times 2 plus 5 times 0, and that's going to be 10. Okay, so we do this and we get a 2 by 4 matrix. So multiplication is straightforward, it's cumbersome for people, it's easy for computers. It's a little bit of a high order of complexity, but it's pretty easy to code up. It's a bunch of nested loops. If you want to write 3 or 4 nested loops, this is your goal. All right, so why does this pop up in engineering? Because in engineering, we have simultaneous equations we want to solve. And it turns out we can write this as a matrix equation, where we put our coefficients over here, and we put our x, y, z over here, and we put our 15, 10, 1 over here. And if you do the matrix multiplication, 3 by 3 times 3 by 1, that should give you a 3 by 1 matrix, which is what we have over here. Well, this multiplication actually turns out to be a 3 by 1, where the first row is 2x plus 4y plus 3z. The second row is negative 2x minus y plus z, and the third row is x plus y plus z. And if we set that equal to 15, 10, 1, the only time that this is going to be equal to that is if this is equal to 15, and that's equal to 10, and that's equal to 1. And so if we can find an xyz which satisfies this matrix equation, that xyz will also satisfy this simultaneous set of equations. And then you plug those into your answer sheet, and you're done with KVL, KCL. Yeah. So we can take this system of equations and turn it into a single equation, but where our constants and our unknown are matrices instead of just single numbers. Well, if we think of this as the matrix A, and we think of this as the matrix X, and we think of this as the matrix B, we can write this equation as A times X is equal to B. And we know what A and B are. They're just these particular matrices. And we're trying to find this matrix X. Well, if A and X and B are real numbers, this is easy, right? X is just equal to B divided by A. Here's the bummer. Don't have division for matrices. Not defined. But we do have something almost as good. We have an inverse, but not always. But we do have this idea of A inverse, A with a minus 1 exponent, which has the property that when we take A and we multiply by A inverse, we get this matrix which is 1 on the diagonals and 0 everywhere else. That's called the identity matrix. And if you multiply this by any matrix M, you just get M. So it acts like a 1. Okay, so if we have an inverse for A, here's what we can do. A inverse AX equals A inverse B. A inverse times A is the identity, and the identity times X is just X. So we can take a set of equations, we can write a matrix A, X, and B, and if we can find an inverse for A, we just multiply by B, we've got our answer. And this, by the way, is not necessarily the same as B times A inverse. Multiplication is not commutative. So this is what we would do in plain old algebra. But in matrix algebra, we have to be careful about the order of things. Yeah, and how does your calculator do it? It's doing this, right? So your calculator is actually using matrix math to solve those equations.
Can you explain that identity matrixing?
Yeah, so I skipped that earlier, but it turns out if you take like A, B, C, D, and you multiply by this thing, well, what's the upper left element? A times 1 plus B times 0. That's just A. This is A times 0 plus B times 1 is B. This is C times 1 plus D times 0 is C. This is C times 0 plus D times 1 is D. So this acts like an identity. You multiply a matrix by this, and you just get the original matrix back. And if it's a 3 by 3 matrix, the identity matrix is this. And I can post or pre-multiply, and it won't change a matrix. So it's like a 1, but it's called big I. All right, so punchline here. I got 4 minutes left. Punchline here. If you can invert a matrix, you can solve systems of equations. Right? Inverting a matrix is just finding a matrix such that when you multiply by your original matrix, you get the identity. So how do you find an inverse? Well, one way to do it is by solving a system of equations. But that doesn't really help us. But there are other things you can do. You can use a method called determinants. And it's a multi-way bifurcating tree of work. To find the inverse of a 3 by 3 matrix, pretty straightforward. To find the inverse of a 10 by 10 matrix, really painful, huge amount of work. To find the inverse of a million by million matrix, now you're talking supercomputers and research. But if you can do this, if you can invert matrices efficiently, you can rule the world. Because everything is driven by this, right? Wall Street, medical research, all of this stuff comes out of the ability to basically invert matrices. There's a reason that a lot of the benchmarks that are used to compare the performance of different supercomputers are really just calculating inverses of matrices, because that's kind of the quintessential task of a modern machine. And you can do all kinds of things that basically drive the engines of our world by solving simultaneous equations, which is just finding inverses of matrices. It's a really hard problem. And it spawned a lot of research in computer science and in mathematics. But mostly we just use our calculators and say, give me the inverse. And MATLAB is great at this. You can just say matrix caret minus 1 gives you the inverse, which is why you can use MATLAB to solve your KVL, KCL equations in the end. All right, so Monday we will start talking about mathematical induction. So we're going to go back to propositional logic, but we're going to tie it into programming in a critical way. All right, have a great weekend. I will see you on Monday.